Hello AP Physics students. This is the second video in the series for the Chapter 2 notes. In this video I'm going to be going over the next 5 slides, slides 7 through 11 in your note packet. So you want to follow along and fill in your notes as we go. In the previous video we just kind of did a review of basic physics concepts. What I want to spend some time in here in this video are sections 1 and 2 in Chapter 2 on advanced linear motion. And particularly I want to give some attention to a little bit about graphs, particularly position time graphs, and I want to spend some time talking about an introduction to understanding some calculus and how it is attached to some of these graphs in the form of understanding derivatives in particular. So let's take a look here at position time graphs. You can see from this image, which is in your book, that when you're dealing with a position time graph, of course, you're graphing position in its standard unit of meters on the vertical axis, and you're graphing time on the horizontal axis. And in doing so, what you're really doing is you are finding a way to indicate the starting position of an object, its final position, and therefore on the vertical axis, you're really expressing a change in position. You can see that here. All right? And then on the horizontal axis, you're indicating some starting time, which is almost always 0, which really expresses the moment you started paying attention to this object. It could have been moving at some negative time in the past, but we weren't paying attention to it until t equals 0. And then moving forward, positive time is the time in the future. The only time we have negative time is when we're looking backwards in time. So here we can see you're going to start paying attention to the object at time 0, but a specific interval of time that you're interested in might, be a starting time, an ending time, and then again, this time interval, delta t, is the change in time we're interested in. The most important thing about these position time graphs is that the slope of a position time graph, the rise over the run, gives you the displacement over the time, and that slope represents the velocity. The question is, does it represent the average velocity or the instantaneous velocity, ideas that we reviewed in the last video? Well, that's kind of a tricky question. Here you can see in this graph you have 2 distinct times, and the slope of the line between those two is actually going to be your average velocity. And we indicate average velocity by putting a line over the letter V. The average velocity, you can see, is not necessarily going to be the same as the slope anywhere else along the way. You can see that the slope at any particular instant of the object's actual motion may have been faster or slower than the average over that time. But when we're considering the average velocity, it's always going to be the slope of a line between any 2 points on a position time graph. The instantaneous velocity is going to be the slope at a specific point on that graph. Instantaneous velocity then lends itself to a common algebraic idea, the idea of a limit, which leads us to our first real calculus idea in this course. What we're really saying, and you can kind of see this in these pictures, is that if you're looking at a big enough time interval, the average velocity is easy to figure out because these 2 points are so far away from each other in time that the average velocity is likely to differ greatly from the actual velocity of that object at several moments or instants in between. It's instantaneous velocity along the way. As those 2 points become closer and closer together in time, then what we find is that we actually we're describing a limit. As the time gets closer and closer to a very specific instant in time, as that time interval shrinks to where it's not discernible as a long time interval between 2 points in time, but it actually becomes a split second in time, then we end up with the slope of that curve at a very specific moment in time, which we often call the slope tangent to the curve. This is an idea that we use in calculus to describe something called a derivative. All right, and derivatives are something you're probably doing in calculus right now. If you're taking a first calculus course, it's something you're probably getting into right now. If it's something you've had a calculus course before or a pre-calculus course, you may be familiar with it. But essentially, this notation right here describes this change in thought from what is a limit versus what is a derivative. Remember, this triangle actually is the Greek letter delta, and it's actually a capital D. In fact, if you kind of turn that triangle on its side, it kind of looks like a capital D that we use today. Delta means changing, all right? But this is a capital delta. It means a big change in over a long period of time or a large interval. The actual lowercase d also is a delta. That's actually the Greek letter delta. It's just a lowercase delta. And it also means change in, but it means teeny little changes in instead of really, really big changes in. So when we see this notation right here, what that actually says is, as we look at teeny, teeny little changes in position with teeny, teeny little changes in time, we should develop an idea of the instantaneous velocity. And that's really what we're seeing here in these graphs. This would be more of a big delta x, big delta t kind of graph, because the distance between these 2 points in time and the distance between these 2 points of position are so large that you could really treat it algebraically, the old version of average velocity. This here you can see, and probably even more so here, the difference between those 2 points in time is so small that the difference in those two positions becomes really, really small. And so what we end up with is instantaneous velocity, which is still changes in position over changes in time, but instead of really big changes in position over time, we're seeing teeny little changes in position over teeny little changes in time. That's a pretty basic explanation of the calculus behind a derivative, behind changing slopes over really, really, really small amounts of time. This is where you start to see this idea of instantaneous velocity really kicking in, is when you start looking at the slopes tangent to the curve. I highly recommend that you visit the following link, all right? This is one of those FETs that you can find right in your e-text. If you go to www.masteringphysics.com and you click on the little picture that says e-text, and then in the e-text you find the little box that says FET. You can mouse right over it, it'll tell you which FET it is. You want the one called the Moving Man. So this is the Moving Man FET. And what this does is it allows you to experiment a little bit with how, when you change these sliders for position or velocity or acceleration and then hit play, it allows you to see how he moves, and it gives you some options for viewing how these graphs are produced by his motion. When you do that, I think it really will help you come to a better understanding of instantaneous velocity and its relationship to position-time graphs. Just remember that the slope of any position-time graph will always give you velocity, and the slope of any velocity-time graph will always give you acceleration. That's a very important thing to remember, all right? And I think you need to spend some time with this. One of the tutorial problems that I've put on the website for you is a Moving Man FET tutorial, and it's terrific, but it's long. I think it budgets about 30 minutes for it. And it might take you that long, because I think to really play with it and answer that question will help you understand these graphs a great deal. So I highly recommend it. Let's take a look at the example in your book that deals with average and instantaneous velocity. This is example 2.1, and you'll find it on pages 40 and 41 in your text. Here what you can see is it describes a cheetah that's crouched 20 meters to the east of an observer's vehicle. Right there, what they're doing is giving you a point of reference. And here you can see in my graphic, there's the vehicle, and here's your cheetah. I really recommend that you do this, that you draw pictures when you're looking at questions like this to really help you understand visually what's going on. and it says that this cheetah is going to charge an antelope, and that antelope, when it charges, begins to run along a straight line, and during the first 2 seconds, the cheetah's coordinates, its position, varies with time according to a function, and here you can see the function that it's dealing with. It could be described as, and I'm getting this right from here, 5t squared plus 20. That describes this motion. I just want you to think about what that graph would look like. Is this likely to be a line, or is this likely to be a curve? Well, it sounds to me like it's a curve because it doesn't have that normal line description to it. Because there's an exponent, we're probably dealing with a graph that's parabolic. And in doing so, it kind of tells us that our cheetah is accelerating. When you see curves on position time graphs, you're looking at accelerations. When you see lines, you're looking at either constant velocities or no motion whatsoever if they're completely horizontal. So what they're asking you to do here in this particular problem is to find the displacement from the period of t equals 1 second and t equals 2 seconds. So here you can see from our picture that right in here is where we're looking for the displacement. All right? Well, you know, this isn't actually that difficult. Position time functions, you know, essentially what we're asking you to do is to insert whatever number they're giving you there. So, you know, where is he after 1 second? Well, you know, this is going to be 25 meters. You know, that's his position. Remember, his initial position right here was 20 meters. He started 20 meters to the east. So that means, you know, in that first second, he moved 5 meters. Where is he at in his second of motion? Well, now, again, we're just plugging in some numbers. So after 2 seconds, he should be located about 40 meters away. You know, so for part A, if we want to know the displacement is actually the difference between this starting and ending point. So since he was at 25 meters after 1 second and 40 meters after 2 seconds, he's traveled 15 meters in that 1 second. This is a pretty good use of what the math looks like, and this really doesn't describe a graph at all. But here, the next thing they do is they say, well, find the average velocity during that time interval. When we start considering average velocity, what we have to consider, is that the average velocity is going to be your displacement over time. Since we know he moved 15 meters to the right and he did it in 1 second, then his average velocity must be about 15 meters per second. It just makes sense during that time interval. But how does that differ from instantaneous velocity? When we think about this, what we can say is that his instantaneous velocity is going to be the derivative of whatever that position time function is. Now, one of the things I didn't get into is that when you find derivatives, there's a certain way of going about that. But what it means is, what we want to be able to do is take this and turn it into this. All right, we're going to take position time and turn it into velocity time by taking the derivative. Now, there's a simple rule for that. When you take derivatives, you're just going to multiply this exponent by whatever's in front of it. So 2 times 5 is 10. Then subtract 1 from whatever the exponent is. 2 minus 1 is 1. So this is going to be 10t to the first. And this was actually 10t to the first already, so it's going to be 10t, 1 times 20, is going to be 20t, and then 1 minus 1 is 0. Well, anything t to the first is just going to anything t to the 0 is just going to kind of fall off. So what we've got is the velocity time function is just 10t. So his instantaneous velocity at the beginning must be 10 meters per second, and his instantaneous velocity at the end of that time must be 20 seconds. This might take some getting used to, and you can ask me questions in class if you need to.